Quantum mechanics. Quantum mechanics is a fundamental theory in physics that describes the physical properties of nature at the scale of atoms and subatomic particles. It is the foundation of all quantum physics, including quantum chemistry, quantum field theory, quantum technology, and quantum information science. 1. Wave-particle duality. Wave-particle duality is a fundamental concept in quantum mechanics that reveals how particles such as electrons and photons can exhibit both wave-like and particle-like properties. For instance, in the double-slit experiment, electrons create an interference pattern typical of waves when not observed, but act like particles when measured. Similarly, light behaves as a wave in phenomena like diffraction, yet demonstrates particle characteristics in the photoelectric effect, where it ejects electrons from a metal surface. This duality is essential for understanding quantum phenomena, as it shows that particles can exhibit different behaviors depending on the experimental setup. 2. Quantization. Quantization is a fundamental concept in quantum mechanics that describes how certain physical properties, such as energy, can only take on discrete values rather than a continuous range. This idea was first introduced by Max Planck in 1900 to explain blackbody radiation, where he proposed that energy is emitted or absorbed in discrete units called quanta. For example, in the context of light, these quanta are known as photons. Quantization helps explain phenomena like the photoelectric effect, where light must have a minimum energy, or quantum, to eject electrons from a metal surface. This concept is crucial for understanding the behavior of particles at the atomic and subatomic levels. 3. Uncertainty. Principle. The uncertainty principle, formulated by Werner Heisenberg in 1927, is a fundamental concept in quantum mechanics that states it is impossible to simultaneously know both the exact position and exact momentum of a particle. This principle highlights the intrinsic limitations in measuring quantum systems, where increasing the precision in measuring one quantity leads to increased uncertainty in the other. For example, the more precisely we determine an electron's position, the less precisely we can know its momentum, and vice versa. This principle is not due to limitations in measurement technology, but rather reflects a fundamental property of nature at the quantum level, emphasizing the probabilistic nature of quantum mechanics. 4. Superposition. Superposition is a fundamental principle in quantum mechanics that describes how a quantum system can exist in multiple states simultaneously. Imagine a particle, like an electron, that can be in two different places at once. This is possible because, in the quantum world, particles have wave-like properties. When these waves overlap, they create a superposition of states. For example, an electron can be in a superposition of being in two different locations or having two different energies at the same time. This concept is famously illustrated by Schrödinger's cat thought experiment. Imagine you have a cat inside a sealed box. Along with the cat, there's a vial of poison, a radioactive atom, and a Geiger counter. The setup is such that if the Geiger counter detects radiation, which happens if the radioactive atom decays, it triggers the release of the poison, killing the cat. If no radiation is detected, the cat remains alive. According to quantum mechanics, until we open the box and observe the cat, the system is in a superposition of states. This means the cat is simultaneously alive and dead. It's only when we open the box and observe the cat that the superposition collapses into one of the two possible states. The cat is either alive or dead. Schrödinger devised this scenario to question the Copenhagen interpretation of quantum mechanics, which suggests that particles don't have definite states until observed. Superposition is crucial for the development of quantum technologies, such as quantum computers, which leverage this property to perform complex calculations more efficiently than classical computers. 5. Entanglement. Entanglement is a fascinating phenomenon in quantum mechanics, where two or more particles become interconnected in such a way that the state of one particle instantly influences the state of the other, no matter how far apart they are. This connection persists even when the particles are separated by vast distances. For example, if two electrons become entangled, measuring the spin of one electron will immediately determine the spin of the other, regardless of the distance between them. This seemingly spooky action at a distance, as Einstein described it, challenges our classical understanding of physics. Entanglement is not just a theoretical curiosity. It has practical applications in quantum computing and quantum cryptography, where it enables secure communication and powerful computational capabilities. Historical development quantum mechanics developed in the early 20th century to explain phenomena that classical physics could not. Max Planck's quantum hypothesis, 1900. Max Planck's quantum hypothesis, proposed in 1900, revolutionized our understanding of energy and radiation. Planck suggested that energy is not emitted or absorbed continuously, but rather in discrete packets called quanta. This idea emerged from his work on blackbody radiation, where classical physics failed to explain the observed spectrum. Planck introduced the concept that the energy of these quanta is directly proportional to the frequency of the radiation, expressed by the formula A toward E, E, from A toward E, H nu, where A toward E is energy, Re toward E is Planck's constant, and from E toward nu is frequency. This hypothesis laid the groundwork for quantum theory, fundamentally changing how we perceive atomic and subatomic processes and leading to significant advancements in physics. Einstein's photoelectric effect, 1905. Einstein's photoelectric effect is a pivotal concept in quantum mechanics that explains how light can eject electrons from a material. When light shines on a metal surface, it can cause electrons to be emitted, but only if the light's frequency is above a certain threshold. This phenomenon couldn't be explained by classical wave theories of light, which predicted that light of any frequency, given enough time, should eventually eject electrons. Einstein proposed that light consists of discrete packets of energy called photons. Each photon has energy proportional to its frequency, given by the equation E chan h anu, where E is energy, h is Planck's constant, and in nu is frequency. When a photon hits the metal, its energy is transferred to an electron. If the photon's energy is sufficient to overcome the electron's binding energy, known as the work function, the electron is ejected from the metal. The excess energy becomes the kinetic energy of the ejected electron. This explanation not only accounted for the threshold frequency, but also showed that the kinetic energy of the emitted electrons depends on the frequency of the incident light, not its intensity. Einstein's work on the photoelectric effect provided strong evidence for the particle nature of light, and earned him the Nobel Prize in Physics in 1921. Niels Bohr's model of the atom. 1913. Niels Bohr's model of the atom, proposed in 1913, was a groundbreaking advancement in our understanding of atomic structure. Bohr suggested that electrons travel in distinct circular orbits, or shells, around the nucleus, similar to how planets orbit the Sun. Each orbit corresponds to a specific energy level, and electrons can jump between these levels by absorbing or emitting energy in the form of photons. This model successfully explained the spectral lines of hydrogen by showing that light is emitted when an electron transitions from a higher energy orbit to a lower one. Bohr's model was a significant step forward from earlier atomic models, incorporating quantum theory to describe atomic behavior more accurately. Although it has since been superseded by more complex quantum mechanical models, Bohr's model remains a fundamental concept in the study of atomic physics. Heisenberg's uncertainty principle. 1927. Heisenberg's uncertainty principle is a fundamental concept in quantum mechanics that states there is a limit to how precisely we can simultaneously know certain pairs of physical properties of a particle, such as its position and momentum. Formulated by Werner Heisenberg in 1927, the principle asserts that the more accurately we determine a particle's position, the less accurately we can know its momentum, and vice versa. This inherent uncertainty arises because particles exhibit both wave-like and particle-like properties. For example, if we know the exact position of an electron, its momentum becomes highly uncertain. This principle challenges our classical intuition and has profound implications for our understanding of the microscopic world, emphasizing that at a quantum level, nature is inherently probabilistic rather than deterministic. Schrödinger's wave equation, 1926. Schrödinger's wave equation is a cornerstone of quantum mechanics that describes how the quantum state of a physical system changes over time. Formulated by Erwin Schrödinger in 1925, this partial differential equation governs the behavior of particles at the quantum level through the wave function. The wave function provides information about the probability of finding a particle in a particular state or location. By solving Schrödinger's equation, we can predict the energy levels, positions, and momenta of particles in a system. This equation is essential for understanding atomic and subatomic processes and has wide-ranging applications in fields such as chemistry, physics, and material science. It bridges the gap between classical mechanics and quantum mechanics, offering a comprehensive framework for studying the behavior of particles at the smallest scales. Mathematical framework. Quantum mechanics relies heavily on mathematics to describe the behavior of particles. Key equations include Schrödinger equation, describes how the quantum state of a physical system changes over time. Heisenberg's matrix mechanics, an alternative formulation of quantum mechanics using matrices. Dirac equation, combines quantum mechanics and special relativity to describe the behavior of fermions. Applications. Quantum mechanics has numerous applications in modern technology and science, including semiconductors, the basis for modern electronics, including transistors and diodes. Quantum computing uses quantum bits, qubits, to perform computations much faster than classical computers for certain problems. Medical imaging, techniques like MRI, rely on principles of quantum mechanics. Lasers operate based on the principles of quantum mechanics. Philosophical implications. Quantum mechanics challenges our classical understanding of reality. Concepts like superposition and entanglement suggest that particles can exist in multiple states simultaneously and be instantaneously connected across vast distances, leading to philosophical debates about the nature of reality and observation. In conclusion, quantum physics has revolutionized our understanding of the microscopic world, revealing a universe that operates on principles vastly different from classical mechanics. Concepts such as superposition, entanglement, and the uncertainty principle challenge our traditional notions of reality, highlighting the probabilistic nature of quantum systems. Max Planck's quantum hypothesis and Einstein's photoelectric effect laid the groundwork for this field, while Niels Bohr's model of the atom and Schrödinger's wave equation provided deeper insights into atomic and subatomic behavior. These foundational ideas have not only expanded our theoretical knowledge, but also paved the way for practical advancements in technology, including quantum computing and cryptography. As we continue to explore and understand quantum mechanics, we unlock new possibilities for innovation and a deeper comprehension of the universe's fundamental workings. Thank you for watching. Please remember to subscribe, like this video, and share it with your friends. Your support is greatly appreciated.